Here's once again, let's recall the definition of continuity. If I have a function f, we say that f is continuous at some number a if two conditions are satisfied. Condition number one is that f is defined at a, so f of a is defined, and remember that means that a is in the domain of f, right? And two, the limit of the function f at a, so the limit of f at a is the same as the value of the function f at a. Okay. Let's look at an example. Let's say I have the function f of x, which is equal to x squared multiplied by sine of 1 over x. Notice that this function is continuous at 0. Is it continuous at 0? No, because the function is undefined at 0, right? So f of 0 is undefined, so the first condition is not satisfied for it to be continuous at 0. So f is discontinuous at 0. Let's change it a little bit. Let's take the function g of x, which is the same as the previous function f, x squared sine 1 over x. This is when x is not 0, and the value of the function is 0 when x is equal to 0. What can I say about the continuity of g at 0? Well, now the function g of 0 is defined, right? G of 0 is defined, because what is g of 0? 0. But then I have to check whether the second condition of continuity is satisfied for this function to be continuous at 0. What do I have to do for that? I have to look at the limit at 0 and see if it is the same as the value of the function at 0, right? So what's the limit? What's the limit as x goes to 0 of x squared sine 1 over x? What's the limit of this function? Remember, a long time ago I actually gave you this example, right? By using the sandwich theorem. What was this limit? Even if you don't apply sandwich theorem, intuitively it's clear what the limit should be. I mean, think about what is happening to sine of 1 over x, right? As x goes to 0, sine of 1 over x does not have a limit, right? Sine of 1 over x, it doesn't have a limit, because as x goes to 0, 1 over x goes to infinity, sine value is going to be going between -1 and 1, right? So sine of 1 over x doesn't really have a limit as x goes to 0. However, we know that it's bounded between -1 and 1. The value of the function is always bounded between -1 and 1. However, you're multiplying that by x squared, right? And x squared is clearly going to 0 as x goes to 0, right? So when x is very, very close to 0, x squared is very, very close to 0, and sine of 1 over x is at best 1, right? So the product will be pretty close to 0, right? Am I making sense? So this limit should be 0, and this is equal to the same as g of 0, right? So then I can say that g is continuous. So g is continuous at 0. Is everybody okay with that? Now here's another example. Let's consider the function f of x, which is the function which is the root of x minus 2. And let's recall the graph of this guy looks like the following. So that's how the graph of this guy. Oops, made a mistake, didn't I? I should be shifting the graph of root x by 2 units to the right. So let's fix that, and I'm going to cheat to fix that a little bit. So I am going to move my axis here. So this is the y-axis, this is the x-axis, this is the number 2 right here. Maybe I can also delete this. Okay, so that's the graph of this function. Notice that if I ask you whether this function is continuous at 2, right? What would you say? Is it continuous at 2? Why or why not? Well, first of all, is the function, if I ask you whether this function is continuous at 2, you have to check 2 things, right? One is the function defined at 2? The second thing, is the limit at 2 equal to the value of the function at 2? What's the value of the function at 2? 0, so it's defined at 2. What's the limit of the function at 2? Here's the problem though, right? Because when we say the limit at 2, it has to be the two-sided limit, right? However, it doesn't make sense to even look at the behavior of the function from the left because it's undefined totally on the left side of 2, right? So in this case, this function is not continuous at 2. However, we are going to say that this function is continuous at 2 from the right. Okay? So notice in this case the limit as x goes to 2 from the right side of 2 of this function is of the function f of x is the same as the value of the function at 2, right? So when that happens, we are going to say that the function is continuous at 2 from the right. So f is continuous at 2 from the right. So generally speaking, we say that f is continuous at a from the right if the limit of the function as x goes to a from the right of f of x is f of a. So if the right hand limit at a is the same as f of a, then it's continuous from the right. And if I want to say it's from the left here, right? So if I say it's continuous at a from the left, then I would be replacing this by what? The limit as x going to a from the left of f of x is equal to f of a. Is everybody okay with that? Okay, so here's another terminology we're going to use here. When we say that, suppose when I say f is continuous on an interval from a to b, so we say f is continuous on an interval from a to b if one, f is continuous at every x inside of the interval from a to b. So these are interior points in the interval. And two, f is continuous at a from the right and three, f is continuous at b from the left. The thing is, if I have a function on an interval from a to b, maybe the function is not defined outside of ab. And in that case, if I say that the function is continuous there, it would mean that it's continuous at the end points only from right or left. Okay? So as an example, let's consider a function like the following. So let's say I have a function which looks like this. Whoops. Okay, so let's make a graph again. So let's say here is the number 0, here is the number 1. If the graph looks like that, the value of the function at 0 is 0, the value of the function at 1, let's say this is 2. I'm just arbitrarily making a graph. This function would be continuous between on 0 to 1. Okay. However, notice that if I change the definition, let's say the function is defined by 4 at 1. This is no more continuous at 1 from the left, right? It's not continuous at 1 from the left anymore. You realize that? The limit at 1 from the left is not the same as the value of the function. if I have this graph, then it's not continuous at 1 from the left anymore. But if I have this situation here, then it is continuous at 1 from the left. Is everybody okay with that? So this function, let's call this function f of x, and so this is continuous on 0 to 1. Everybody's okay? Okay. So that's that. There are some algebraic properties that we need to look at. So here's a theorem. If the function f and the function g are continuous at some number a, and c is a constant, then number one, we could say that the function f plus or minus g, the constant c times f, or even f times g, they are continuous at a as well. So what this is saying basically is that if two functions are continuous at a number, then their sum, their difference, their product, their multiples, they are all continuous at a as well. And number two, their ratio function is also continuous at a, but in this case I have to put a condition, provided that x is provided that g of a is not 0. Right? If g of a is 0, then it wouldn't be continuous at a. Okay, so these are the algebraic properties of continuity of functions. So let's do an example here. First of all, suppose that I have the function p of x, which is a polynomial function, and that function is 1 plus 2x plus 3x squared. Just a polynomial function. And I want to know where this polynomial function is continuous. So the question is this function continuous at any number? So let's let a to be any real number. And I want to know if it is continuous at a. Well, p of a is defined, right? P of a is defined. Why? Because we know that the domain of a polynomial function is what? Everything. Okay. What's the limit of the function p of x at a? What's the limit at a of p of x? Well, remember when we talked about limits, we said the limit of a polynomial function can be found by just plugging in the number, right? So we know already that the limit at a is the same as p of a. So both conditions of continuity are satisfied. So that tells you that p of x is continuous at any real number a. So a is any real number here. So so that means I can say that p of x is continuous on the entire real line. Okay, and this is true for any polynomial function. Okay, so anytime you have a polynomial function, you can assume that it's continuous everywhere. Okay, so here's a fact: a polynomial function p of x is continuous on the entire real number line. Okay. How about rational functions? So let's look at an example with rational function. Suppose I have the function g of x, which is the rational function x minus 1 over x plus 2. So this is a rational function. Where is this function continuous again? Well, first of all, g of negative 2 is undefined, right? Is undefined. So g is discontinuous at negative 2. But is it continuous at any other point? Well, let's see. G of x, so g of a is defined for any a not equal to negative 2, right? If a is not negative 2, it's defined. That is, a is in the any other real number is in the domain of the function g. And let's look at the limit of the function g as x goes to a. So what is the limit of the function g of x as x goes to a? Well, that's the same as the limit x goes to a of the rational function x minus 1 over x plus 2. And how do we find the limit of a rational function when the limiting point is in the domain of that function? How do you find the limit of this rational function at a? Remember, a is not negative 2. So when I plug in a, it doesn't make the denominator 0, so I can just find the limit by plugging in. So this will be a plus 2 and a minus 1, right? Which is exactly the same as the value of the function at a, obviously. So what we see is that g is continuous at any a which is not negative 2, right? So g is continuous at any a which is not equal to negative 2. So therefore we can say that g is continuous on the entire real line except at negative 2, right? Except at negative 2. At the end of the day, what we're saying is that if I have a rational function, it is continuous on its domain, right? If you look at what I wrote down there, it's exactly the domain of the function, right? So a rational function is always going to be continuous on its domain. Okay? So a rational function is continuous on its domain. Okay. Okay, so now we know how to find the intervals where if a rational function is continuous. So here's an example. let's say I have the function h, which is given by 1 plus x plus x cubed minus 3 divided by x minus 2. Okay, that's the function that I have. Let's say the question is determine where h is continuous. Determine where h is continuous. How do I decide that? Well, I'm going to view this into the function in two parts. This guy and minus this guy. The first collection of terms is a polynomial, right? And we know that it's continuous where? Everywhere. The other guy, the rational part, the rational function part there, it's continuous everywhere except at 2. So can I then say that both of this, the polynomial and the rational, both of them are continuous everywhere except possibly at 2? One of them is not, right? So remember one of the theorem that I gave, if two functions are continuous somewhere, then their sum or difference will also be continuous there. So by using that, I can say that because both of them are continuous everywhere besides 2, right, their difference will also be continuous everywhere besides 2. Right? So if I invoke that, I could say that h is continuous on everywhere except at 2. Now, one thing you might want to realize that the function that I have here is in fact a rational function. You realize that? Is that the ratio of two polynomials, the function h? Note that I can put a 1 underneath this polynomial, right? And then I can combine the two into one fraction, right? So this is actually a rational function, and that's the domain of the rational function, right? And we know that a rational function is continuous on its domain. So I could have said that as well, instead of saying the way I said it. Okay. Is everybody okay with that? Any questions on that? Any questions at all? Okay, I think I want to stop right here talking about section 1.8. We need one more lecture to finish 1.8, probably half an hour next time to finish 1.8. So again, 1.8 will not be on your exam tomorrow, but everything else that I gave on the homework sheet last time will be on the exam. Okay, so the rest of the time, what I want to do is talk a little bit about the exam. So, what can I say to you about your first exam? So, exam 1. Okay, so one of the problems that I usually ask, or I definitely will ask, is find the domain of a function. Okay, find the domain of a function. So for example, let's say find the domain of the function which is given by x squared plus x minus 2. I mean, I just made up an example here, but I'm not necessarily going to give you this function. So find the domain of, so in fact, I'm going to give you two functions and you have to find their domains. Okay? So you'll be given two functions here. So there will be like a part A and a, maybe instead of a part A, maybe something like this, okay? And two, sketch graph by using transformations. So basically I'm going to give you a function for, let me give you an example. Let's say you have the function f of x, which is 3 times the root of 2x minus 2. I don't know, I'm just making up something. So you have to start out with a familiar function that you know how to draw, and then show me this, what transformations you applied to obtain the graph of this guy. So for example, in this case you have to start with the graph of what? Root of x. You start with the graph of root of x, and then you apply different transformations and come up with the graph of this function f. Okay? That is, shifting upward, downward, left or right, stretching or compressing, things like that. Okay? And you have to show me what shifts or other transformations you're applying. So that's the second question. Third, find the horizontal asymptote and the vertical asymptote of a function, let's say f of x is equal to x squared minus 2x plus 1 over x squared plus x minus 2. So this is an example I did in the class. But I'm going to give you one function and you have to find out the horizontal and the vertical asymptotes of that function. For find limits. Find limits. Probably 3 to 4 of them. So maybe 3 problems, maybe 4 problems on limits. So obviously I am going to be asking at least one limit problem. So the limit problem is find the limit as x goes to 1 or infinity or negative 1 or 0, things like that. So you should expect one question from 1.5, at least one from 1.6, and at least one, in fact exactly one from 3.4. Okay. So that's what you would expect there. Do I have the text with me? Okay, I'm going to say a few words on that in a bit. So let me move on to something else. Number 5. This is 2. Yes, number 5. Number 5. What can I say? It's easy. number 5, I don't want to say too much about it, but it's going to be something easy if you know what to do. So it's mainly on function operations. Okay? So I'm going to tell you 2 of them. Here, one is, one of the problem here will be, there will be probably 4 parts or 4 to 5 parts on it. But these are very, very quick parts. If you know what to do, there's only one line answer. Okay. So this is there might be 4 parts here: A, B, C, and D. And what I'm looking at, 2 of them that I'm going to look at is given 2 functions, find the composition of that. Find the composition function. So find the composition of 2 given functions. Okay, that's one of them. So find the composition of 2 given functions. Also, the inverse of this question, the opposite of this question, which is given a function, find. So this is given a function, find 2 simpler functions such that, so given a function, let's say you're given the function h, okay? Given a function h, find 2 simpler functions f and g such that h is the composition of f and g. So that's what I mean. So this is sort of the opposite of the other one, because of the other one you're given 2 functions, find the composition, and this is given a function, find 2 functions whose composition will give you that function. Is that clear? So that's it. I think, yeah. And of course there are other things. There will be 2 or 3 other parts in that problem. Again, these are not hard, it's just easy. But sometimes people still do make mistakes on them, even though they are easy, because, well, they didn't do their homework problems, I guess. Again, this would be on operations of functions. Any questions on anything? Yes. Any questions at all? Do you feel like is there any parts on this discussion of the exam 1 that you want me to discuss more? Do you want me to do an example of one of the questions that you see here? Problem 3. Find the vertical and the horizontal asymptotes. Okay, so let me see. Okay, so find the vertical and horizontal asymptotes of a function. So let's look at the function x plus 2 divided by x squared minus 5x plus 6. So let's say I have that. And I want to find the horizontal and vertical asymptotes. To find the horizontal asymptote, what you have to do is what? You take the limit of the function as x goes where? As x goes to infinity. You want to know the terminal behavior of the function when x is big. And what's the limit? What's the limit? Y. This is the limit of x over x squared, and that is 0. Right? Well, maybe I should write one more line here. This is the limit as x goes to infinity of 1 over x, which is 0. Why can I say that the limit is the same as x over x squared? Because I said when x is big, the behavior of a polynomial is determined by the dominating term. So you take the dominating term in the numerator and the denominator, and the limit will be determined by that. This is only when x goes to infinity and when you have a rational function. Okay, so that's that. So y equals to 0 is a horizontal asymptote, right? Y equals to 0. Sometimes people write x equals to 0 is the horizontal asymptote. Horizontal asymptote, by the name of it, it's a horizontal line. Okay, so it should not be x equals to 0. You need to also look at the limit as x goes to negative infinity of the function. Okay. However, in this case, you're not going to get a different number. In this case, that limit is still 0. So you get only one horizontal asymptote. If the limit at negative infinity was different, you would be getting another horizontal asymptote. Okay, what are the vertical asymptotes? Well, you get x plus 2 divided by x squared minus 5x plus 6, and that's the same as x plus 2 divided by x minus 2 times x minus 3, right? I can factor out the denominator this way. Now you ask yourself, you try to find values of x where the limit of the function is either infinity or negative infinity. Find values of x where the limit of the function is infinity or negative infinity. So what are they? Well, notice that at 2, when x is, for example, when x goes to 2 from the right, for example, what's happening? Well, the denominator goes to 0, the numerator goes to a non-zero number, right? So what did I say? When the numerator has non-zero limit, the denominator has limit 0, the ratio will have limit plus or minus infinity. In this case, I don't have to worry about whether it's plus or minus, because the limit is not the either way. I have a vertical asymptote. Okay? So I'm going to have a vertical asymptote in this case at 2, and I also have a vertical asymptote at 3, the same way. Okay. Basically, these are the places where the denominator vanishes, but the numerator doesn't vanish at those numbers. Okay, that's important, that the numerator does not vanish at 2 or 3. Is everybody okay with that?
Why is it that where the numerator vanishes at
Well, here's the one example. Let's say I have x minus 2 and x minus 3, and here instead of having whatever I had before, let's say I have x minus 2. Then what happens is that the value of this function is the same as the value of 1 over x minus 3, right? As long as x is not 2. So now the limit of this function, the limit of this guy at 2 is no more infinity. the limit of this guy at 2 now is actually 1 over 2 minus 3, which is negative 1. Am I making sense? So because in the numerator you have x minus 2, denominator you have x minus, they cancel out. The limit at 2 is no more infinity or negative infinity. Okay. When you look at the limit problems in 1.5, 1.6, 3.4, as you do the problems, think about the techniques that you are applying. You know, what happens when you get 0 over 0? What do you do? What do you have root functions? What do you do? When you have 0 over 0, can you factor out? Things like that. When you have a non-zero limit divided by a zero limit, what happens? Those are the things that you want to remember, okay, as you do your problems. And think about what techniques you're applying for what type of problems, right? Or what type of limits. Okay, I'll see you tomorrow.